Netflix processes over 1 billion user interactions daily, yet a staggering 90% of machine learning projects fail to make it to production due to data quality issues. Here's what most engineers get wrong when designing ML data pipelines. Keep this in mind. We'll see why this matters when we discuss scaling and reliability. By the end of this video, you'll know exactly how to build a robust and scalable pipeline for ingesting, validating, and engineering features for machine learning models.
Let's define the scope of our ML data pipeline. Functionally, we need to ingest data from various sources, validate its integrity against predefined rules, transform it into usable features suitable for model training and inference, and store these features in a feature store. Non-functional requirements include scalability to handle billions of events daily, low latency for feature retrieval to serve real-time predictions, and high data quality to ensure model accuracy. A clarifying question: do we need real-time feature engineering, or is batch processing sufficient? Let's assume batch for now to simplify the design, but we'll consider the real-time implications later. We'll also need a rate limiter to protect our API from abuse. The secret is to design for failure from the start.
Let's estimate the scale of our data pipeline. Remember the 1 billion daily interactions? This is where that matters. Assume 1 billion events per day are ingested. That's roughly 11.5K events per second, 1B over 24 times 60 times 60. If each event is 1 KB, we're looking at 11.5 megabytes per second of data ingestion. For storage, if we keep data for 30 days, that's 1 KB times 1B events per day times 30 days equals 30 terabytes of storage. Bandwidth-wise, if we need to read all the data for a daily feature engineering job, that's 30 terabytes to read in 24 hours, requiring roughly 3.5 gigabits per second throughput. These estimations will guide our technology choices. We'll need to handle this QPS and storage volume when designing our system.
Here's the high-level design for our ML data pipeline. We'll separate the read and write paths for optimized performance. The write path, top, starts with clients sending data to a load balancer, then to an API gateway, post/API/v1/events. From there, data flows to app servers. These servers synchronously write to a primary database, PostgreSQL, with asynchronous replication to replicas. For non-critical operations, we use asynchronous processing. A message queue, Kafka, feeds a worker pool, which writes to an analytics database, ClickHouse. Cache invalidation is shown from the app servers to Redis. The read path, bottom, starts with clients hitting the load balancer, then the API gateway, get/API/v1/features, which checks the cache first. A cache hit returns immediately. A cache miss queries the read replica and populates the cache. We also have side components, a CDN for static data, a rate limiter for API protection, and monitoring for system health. We use Kafka because it provides ordering guarantees and replayability, which are crucial for data consistency. SQS was considered, but it lacks these features. Here's the twist. Most engineers overlook the importance of data lineage tracking at this stage. This architecture is designed to handle the scale of 1 billion daily interactions.
Now let's dive into the core logic of the data validation service. We'll use Debezium for change data capture from our operational databases to ingest data. Data validation is crucial. We'll implement schema validation to ensure data conforms to expected formats. We'll also perform type validation to check data types, and range validation to ensure values fall within acceptable boundaries. A common candidate mistake is stopping here, but we also need custom validation rules for business logic. For example, validating that a user's age is within a reasonable range. We'll use great expectations for this. The data structure will be a directed acyclic graph, DAG, where each node represents a validation rule. This allows us to easily add or remove rules. We need to ensure item potency in our validation service. If a validation job fails and retries, we don't want to double count errors. We can achieve this by assigning each event a unique ID and tracking which events have been validated. Now, at this point, your interviewer will push back. Why not just use a simple if-else statement for validation? The reason is that a DAG provides flexibility and scalability. We can easily add new validation rules without modifying existing code, and the DAG can be executed in parallel for faster processing. We chose Great Expectations because it provides a declarative way to define validation rules and integrates well with our data pipeline. A trade-off is that it adds complexity compared to writing custom validation code. We use a DAG because it allows us to define complex validation workflows with dependencies between rules.
Alternatives like simple lists of rules don't allow for this level of control. We'll use a Bloom filter to quickly check if an event has already been processed, reducing the load on our tracking system. We can use the Aho-Karasik algorithm to efficiently match multiple validation rules against the incoming data stream. This is especially useful when dealing with a large number of complex rules. The Aho-Karasik algorithm constructs a finite state machine to efficiently search for multiple patterns, validation rules, in the input stream, data. The algorithm's efficiency stems from its ability to process the input stream in a single pass, making it suitable for real-time data validation scenarios. Stop. Think about this. What happens if a validation rule itself contains an error? To simplify complex validation rules, we can use decision tree algorithms. The decision tree algorithm recursively partitions the data based on the values of different attributes, creating a tree-like structure that represents the decision-making process. This allows us to break down complex validation rules into smaller, more manageable steps. We can use the Levenshtein distance algorithm to measure the similarity between the data and the expected schema. This is useful for detecting data drift and identifying potential schema changes. The Levenshtein distance algorithm calculates the minimum number of edits, insertions, deletions, or substitutions required to transform one string into another. This allows us to quantify the degree of difference between the data and the expected schema, providing a metric for assessing data quality and identifying potential issues.
Let's define the data model for our feature store. We'll use Cassandra for its high write throughput and scalability. The schema will include feature name, text, primary key, entity ID, text, primary key, feature value, blob, feature type, text, created at, timestamp, job ID, UUID, parent ID, UUID, and budget consumed, float. Created at and job ID are audit fields for tracking when and how the feature was created. Parent ID enables data lineage tracking, allowing us to trace augmented samples back to their original sources. Budget consumed is for differential privacy, tracking the amount of privacy budget used for each feature. We'll index entity ID to enable fast lookups by entity. Pause and think. What's missing from this schema? We also need a version field to track feature versions and enable rollback if necessary. We use UUIDs for job ID and parent ID to ensure uniqueness across distributed systems. We chose Cassandra because it's a distributed NoSQL database that can handle the high write throughput required for our feature store. Relational databases like Postgres were considered, but they don't scale as well for this use case. We'll use the murmur hash algorithm to distribute data evenly across Cassandra nodes. Murmur hash is a non-cryptographic hash function suitable for general hash-based lookup. It provides good distribution and performance.
Now, let's talk about scaling our ML data pipeline. To handle the volume of 1 billion daily interactions, we need caching. We'll use Redis as a cache aside to store frequently accessed features. On a cache miss, we'll query Cassandra and backfill the cache. This keeps our P99 latency under 50 milliseconds for read-heavy workloads. We'll use replication for both Redis and Cassandra to ensure high availability. For Cassandra, we'll use a multi-data center setup to tolerate regional outages. We'll shard Cassandra by entity ID to distribute the data across multiple nodes. This allows us to scale horizontally as our data volume grows. We might be tempted to use a CDN for feature values, but that's generally not suitable since feature values are dynamic. However, we can use a CDN for static metadata about features. A bottleneck analysis reveals that the feature engineering job is I/O-bound. To address this, we can use distributed processing frameworks like Spark or Flink to parallelize the feature engineering tasks across multiple nodes. We use consistent hashing for sharding to minimize data movement when nodes are added or removed. An experienced interviewer will probe what happens at 10x scale. Here's the key. We'd need to reevaluate our sharding strategy and potentially use a more sophisticated approach like dynamic sharding. We use Redis because it's an in-memory data store that provides low-latency access to frequently accessed features. Memcached was considered, but Redis offers more advanced features like persistence and data structures. We'll use the least recently used, or LRU, eviction policy in Redis to ensure that the most frequently accessed features are always available. Remember the 1 billion daily interactions? This is where caching becomes critical to maintain low latency.
Building on our scaling strategy, for fault tolerance, we'll use redundant components and automated failover mechanisms. If a Cassandra node fails, the data will be automatically replicated to another node. We'll also use a circuit breaker pattern to prevent cascading failures. For monitoring, we'll track key metrics like data ingestion rate, validation error rate, feature store latency, and resource utilization. We'll use Prometheus and Grafana for monitoring and visualization. For alerting, we'll set up alerts for critical events like high validation error rates or service outages. We'll use PagerDuty to notify on-call engineers. The circuit breaker pattern prevents cascading failures by stopping requests to a failing service before it overloads other services. This improves the overall resilience of the system. We'll use exponential backoff with jitter for retries to avoid overwhelming the system. The rate limiter we mentioned earlier comes into play to prevent abuse and ensure system stability.
In summary, we've designed a scalable and reliable ML data pipeline capable of handling 1 billion daily interactions. The key trade-offs were between consistency and latency and between cost and performance. The main bottleneck is the I/O-bound feature engineering job, which can be addressed with distributed processing. Next steps would be to implement real-time feature engineering using a streaming framework like Flink, and to add bias detection and mitigation techniques to ensure fairness in our models. We'll also need to implement a robust rules engine to manage complex validation rules.
If you found this helpful, please like, share, and subscribe for more technical deep dives like this.